Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Let me introduce myself. My name is Laela Nur Fitria. I'm a mechanical engineering student from Sampoerna University. It is an honor for me today to be here, attending the 7th International Conference on Electric Vehicular Technology 2022 to deliver a presentation. Okay. As we know, in engineering design, we should consider about the failure possibility of a design with certain material. And buckling is one of those failure possibilities. So, buckling is instability that leads to a failure mode with a sudden change in shape of a structural component under load. Therefore, in this opportunity, I will present about experimental study on the compression and buckling properties of 3D printed PLA to discuss more on how it can be used for design purpose in manufacturing the electric vehicle part. And nowadays, additive manufacturing, or popularly known as 3D printing technologies, are becoming one of prosperous development prospects in the manufacturing industry. The advanced 3D printing technology has drawn many attention from researchers and engineers. In 3D printing, multifarious material that can be used, such as metals, polymers, ceramics, composites, and smart materials. So from those materials, the 3D printed object is widely used in various engineering applications, including the automotive industry of electric vehicles. The demand was gradually increasing to support the production and development of electric vehicle components such as the body, fairing, mirror casing, bushing, or driver seat. So, there are many researchers who have considerably reported studies on the mechanical properties and behavior of 3D printed PLA, such as the effect of virgin and recycled 3D printed PLA filament to its tensile yield strength, elastic modulus, shear yield strength, and hardness. And there is also the influence factor of layer height, filament width, infill density, layer orientation, printing velocity, and infill pattern in 3D printed PLA through bending and fatigue testing. So, some of these prior studies have been done to investigate the 3D printed compressive properties. However, studies on compression and buckling properties and behavior of 3D printed PLA column structure have not been comprehensively understood. Furthermore, the effect of infill pattern and infill density on the critical buckling load has not been extensively explored. Therefore, the research objective of this work is to investigate the compression and buckling properties and behavior of 3D printed PLA column structures with concentric infill pattern and various infill densities to be used for mechanical design of electric vehicle structure. We move on to the next slide. So for the specimen preparation, first, CAD model is created using SolidWorks. Then, CAD model is converted into STL format. After that, slicing of STL model into thin layers using Ultimaker Cura. Then, the STL file is converted into G-codes. After that, the G-codes is inserted using SD card to the Anycubic i3 Mega 3D printer, and then the FDM process is done in manufacturing the 3D printed PLA column structure. So, 3D printed PLA column structure is manufactured by 10 mm of diameter with this following column length and this following printing parameters. Next, in this work, compression test is conducted by using Test Resource 313 Family Universal Testing Machine with a STM D695 standard method test to analyze the compression and buckling properties of 3D printed PLA column structure. Then, the XY software is utilized to insert the dimension of column structure, logging rate, and control rate for the compression test. And after that, the top and the bottom part of the column structure is greased by petroleum jelly so the compression test can be started. And from the test, the XY software provides some data about applied load, stress, and displacement that experienced by the column structure. So we move on to the next slide. In this work, buckling property that is considered are Johnson and Euler formula. From this following formula, the value of yield strength and Young's modulus are needed to calculate the critical buckling load. The next, in here, the stress-strain curve of 3D printed PLA column structure is determined by dividing the load with displacement on each curve. And Young's modulus value is calculated by the maximum tangent modulus value. And after analyzing the result from compression test, it shows that higher infill densities resulted in larger value of Young's modulus and yield strength. That's shown in this following table. So next, from here, the critical buckling load of 3D printed PLA column structure is determined by largest value of load or first peak on each curve. And once the buckling happened, the slope of load displacement curve decreased dramatically. Next, and this is the result of load displacement curve from 3D printed PLA column structure with 100, 160, and 200 millimeters of column length. So from the load displacement curves here, the critical buckling load is analyzed for each column line with different infill densities. And by displacement, 100 millimeters of column line has longer displacement compared to the 160 and 200 millimeters of column line with the same infill density. Now we move on to the next slide. This is the result where 3D printed PLA column structure with 100 millimeters, 160 millimeters, and 200 millimeters of column length experience buckling during the compression test. And from the table here, 3D printed PLA column structure with higher infill density generates larger critical buckling load. And the longer column length has small critical buckling load compared to the shorter column length. So let's take a look at 75% of infill density, where 100 millimeters of column length has larger critical buckling load around 3,100 newtons than the specimen with 100 millimeters of column length, which is only around 900 newtons. Next, after we identify the critical buckling load, the next step is critical buckling load for every infill density is normalized with the corresponding yield strength, then plotted with the column length as shown in this figure. Then the comparison with the theoretical formula is done. And after that, all specimens showed brittle fracture, except the specimen with 200 millimeters of column length that shows no major fracture without breaking. Okay, we move on to the next slide. In here, the Johnson-Euler buckling formula is compared with the experimental result for various infill density such as 0%, 25%, 50%, 75%, and 100% of infill density, which shown in these following curves. So from here, the Johnson formula observes the buckling load in the shorter slenderness ratio. On the other hand, the Euler formula estimates the buckling load in the longer slenderness ratio. So in these curves, the blue line here represents the Johnson formula. And the red line here in each curves here represents the Euler formula. So both formulas moderately predict the buckling load in more safety area. Thus, it can be used for design purpose. However, some gaps, so there are some gaps in each curve between the theoretical data and the experimental data, and these gaps are still observed. Therefore, it needs further investigation. And now, we arrive in conclusion part. So, from this work, we can conclude that the compression test on the concentric column structure with various column length and infill densities have been conducted by this work to investigate the compression and buckling properties and behavior of 3D printed PLA column structure. The second one, the higher infill density of column structure generates a bigger value of Young's modulus and yield strength. However, the column structure with a longer column length will tend to buckle easily. The third one, all infill densities with 100, 160, and 200 millimeters of column length are observed to be failed due to buckling. And the last one, Johnson and Euler buckling load formulas could moderately predict the critical buckling load of 3D printed PLA materials, although less precisely. Okay, so that's all from me. Thank you for your attention and have a good day, everyone. See you.